It is January. The temperature outside is 11 degrees. The wood stove in the corner of the room is burning hard, hot enough to keep the whole house warm through the night. But 3 hours ago, the power went out, and everything in the house that needs electricity is dark. The phone is dying, the lights are out. The solar panels on the roof are producing nothing. The only thing working is the fire. And somewhere in the back of the mind, a question begins to form. A modern off grid solar system is supposed to solve exactly this problem: $20,000 in rooftop panels, a battery wall in the garage, an inverter humming on the wall. But tonight, there is no sun. There has been no sun all day. The battery bank is discharging, and the panels are sitting dark under a cloudy winter sky. The system that was supposed to provide energy independence is idle on the coldest night of the year. But the stove is doing something that nobody in the room is thinking about. Every surface of that cast iron box is running somewhere between 400 and 600 degrees Fahrenheit. The room behind it sits at 68. Between those 2 points, there is a temperature difference of more than 500 degrees. And a temperature difference, as physicists have understood since 1821, is not just heat. It is electrical potential waiting for the right path to run through. In some older households that had to generate their own power before the rural grid arrived, a small flat device sat directly on that stove surface. A compact stack of alternating metal strips, copper and iron most commonly. No moving parts, no separate fuel. A short length of wire ran from it to a small lamp mounted on the wall nearby. The device looked almost like nothing: a thin plate of metal sitting on a stove. But it was producing electricity from the heat beneath it. That lamp was lit. Not from the grid, not from a battery, from the temperature difference between the stove surface and the cooler air on the backside of that metal plate. The fire heating the room was simultaneously pushing current through a wire. No inverter, no solar panel, no permit, no monthly account. Just two different temperatures, two different metals, and a circuit connecting them to a load. And the bulb glowed. The modern system sitting dark on that roof tonight cost somewhere between $20,000 and $35,000 installed. The device producing light on top of that old stove cost between $3 and $15 in wire and metal. Both are trying to answer the same question. One of them works on the coldest, darkest night of the year. One of them does not. And it is not the expensive one that is working right now. The principle behind that stove device has a name: the Seebeck effect. Thomas Seebeck, an Estonian-German physicist, documented it in 1821. His observation was simple. When a circuit made from two different metals has its two junction points at different temperatures, one hot, one cold, electrical current flows through the circuit. Hot junction, cold junction, two different metals, current in the wire. That is the entire principle. It has not changed since 1821. This is not obscure science. The Seebeck effect is the operating principle behind every thermocouple temperature sensor used in industrial ovens, in jet engine exhaust systems, and in the thermostats of gas furnaces. Whenever an industrial system reads temperature by measuring a tiny voltage in a metal circuit, it is using exactly this effect. The measurement application became standard across industry. The generation application, using the same physics to produce useful electricity, is where the story gets interesting. Here is the problem with a single junction. One connection point of copper and iron at a 500-degree temperature difference produces roughly 6 to 7 millivolts of voltage. That is real. That is measurable. But it is not enough to light a bulb or run a radio. A single junction is a whisper of electricity. Useful for measuring temperature, not yet useful for producing a meaningful load. To get from a whisper to something usable, the junctions have to be multiplied. This is where the thermopile design solves the problem. A thermopile is a series of thermocouple junctions connected so that their voltages add together. Stack 20 junctions and the output is 20 times the voltage of one. Stack 100, and the total approaches the range where small but useful electrical loads become possible. All the hot junctions share one face against the stove surface. All the cold junctions share one face toward the room, one fire, one temperature difference, multiplied across every junction in the stack. Now, here's the detail that separates a device that actually works from one that disappoints. The voltage output is not determined only by how hot the stove surface gets. It is determined by the difference between the hot side and the cold side. If the cold side of the device warms up, now because heat is moving through the assembly faster than the back surface can shed it, The temperature difference shrinks. The output drops. The stove can be burning at full heat, and the device can still underperform because the cold side is the variable that most people overlook. The solution is surface area and airflow on the back face of the device. A corrugated steel fin attached to the cold side gives warm air a large surface to escape from. Natural convection handles the rest. Warm air rises away from the fin. Cooler air moves in to replace it. The cold side stays significantly below stove temperature. No fan, no pump, no coolant circuit, just metal geometry and the direction it faces. The builders who understood this got strong output. The ones who did not got disappointing numbers. The builders who mounted their device flat against a wall with no room for airflow got weak results, and sometimes concluded the principle did not work well. The principle worked fine. Cold side management was the engineering problem, and solving it required nothing more than positioning the device so that room air could circulate freely across the back surface. Getting the hot side right is automatic. The stove handles that without any effort. Getting the cold side right is where the builder either succeeds or does not. What could a simple thermoelectric stove device realistically power? At the output levels achievable from a standard wood stove surface, the honest answer is modest but meaningful. A radio receiver, one or two small lamps, a slow trickle charge into a lead acid battery that would then supply a slightly larger load through the following day. Not a refrigerator, not a power tool, but the loads that mattered most to a household operating without a grid connection. Light, information, and stored reserve power for the next morning. The radio mattered more than it might seem. In an off-grid rural household of the early to mid-20th century, the radio was the connection to weather forecasts, emergency broadcasts, and market prices. A household that could keep a radio running without a utility account had access to information that households without that capability did not. In a farming context, catching the morning weather forecast before cutting hay could be the difference between a successful harvest and a ruined one. The device on the stove was not a curiosity, it was a practical advantage. The thermoelectric generation principle was not exclusive to any single community or tradition. Similar low-power generation approaches appeared in remote telegraph relay stations, where continuous operation mattered and fuel delivery was expensive. They appeared in various off-grid experimental applications, wherever heat was already available and a small electrical load needed to be served without a grid connection. The Seebeck effect does not belong to any one region. It belongs to physics. And anyone working with heat and metals long enough eventually notices what it can do. What ended the widespread practical use of simple thermoelectric stove generators was not a superior technology replacing them. It was the arrival of the rural electric grid, which gradually reached unelectrified farmland across America from the mid-1930s through the 1950s. When grid power became available, the question those devices answered stopped being relevant. The knowledge of how to build one stopped being passed on because the reason to build one had disappeared. Skills that stop being taught rarely survive more than one generation. The modern version of the same operating principle uses thermoelectric modules made from bismuth telluride, a semiconductor material that produces significantly more output per junction than copper and iron. These modules are manufactured and sold today for between $3 and $25 each. Small, rectangular, no moving parts. Place the hot face against the stove surface. Connect an appropriate heat sink to the cold face. The physics running through the device are the same physics Thomas Seebeck documented 2 centuries ago. Stack 4 to 8 modern thermoelectric modules on a stove surface with an aluminum heat sink. On the cold side, and the combined continuous output during an active burn falls in the range of 8 to 25 watts of electrical power. That covers LED lighting, a low-draw radio, and a trickle charge to a small battery bank. The stove runs, the device runs, the battery charges. The lights stay on. Any real installation involving heat sources, electrical connections, and wiring should be assessed by a qualified professional familiar with local codes and safety requirements. The material cost of a working modern stove thermoelectric system, modules, heat sink, basic components, falls between $15 and $40 depending on how many modules are used and the source. A solar plus storage system capable of comparable basic household loads costs between $25,000 and $45,000 installed. The stove system produces power on the coldest, darkest nights of the year. The solar system produces nothing on those same nights. Both facts are true at the same time.
This is not an argument for abandoning solar. It is an argument for asking a prior question. What energy resources are already present in this specific house? What is already being produced and fully discarded? A wood stove running through a long winter is already producing a continuous thermal resource. Some of it heats the house, all of the rest goes up the chimney. The question of whether any portion of that resource can be converted into something else has a clear answer. The question just stopped being asked for 60 years. This system does not work for every household. If the primary heat source is a gas furnace or heat pump, and the wood stove runs only a few times a year, the output is occasional at best. If the stove runs at low smolder temperatures for long periods, rather than active high-temperature burns, the temperature differential narrows and output drops significantly. The honest application is specific. Homes where wood is already the primary winter heat source, where the stove runs hard for hours every day, and where a small supplemental electrical load is worth capturing. What was actually lost when the rural grid arrived was not primarily the device itself. The device is simple enough to reconstruct from first principles. What was lost was a habit of thinking. Looking at a burning stove and asking, what else is this doing? Looking at a flowing stream and asking, what pressure is here? Looking at a south-facing wall in July and asking, what is that surface temperature doing? The grid delivered electricity, and with it, the permission to stop treating the physical environment as a set of energy resources waiting to be read. A wood stove burning on a cold January night is still a temperature difference. A temperature difference connected to the right materials is still a voltage. A voltage is still electricity. The physics have not changed since 1821. What changed is whether anyone in the building is asking what the fire is doing beyond keeping the room warm. And given where utility bills are heading, that question is starting to sound less like nostalgia and more like a straightforward engineering inquiry that should have been asked much sooner. Leave a comment telling us what you would power first from a stove-based thermoelectric system in your home: a radio, a battery charger, LED lights, a phone circuit. Tell us what the first practical load would be, and whether you already heat with wood, or whether this changes how you think about the stove you have. Every comment helps us understand what this channel should investigate next. Subscribe now, because the next investigation in this series follows a device that does something most people consider physically counterintuitive. It moves water from a low point to a high point, using no motor, no electricity, and no external fuel. The only energy input is the water itself, in motion. Old farms used it to fill elevated storage tanks from streams that ran below the house level. It was commercially manufactured for decades. Then, electric pumps arrived. The economics changed, and the device quietly disappeared from most property conversations. The water never stopped flowing. The physics never stopped working. What stopped was the habit of looking at a stream on your property and seeing a resource rather than scenery. That habit is what this channel is trying to put back, one old system at a time, one forgotten question at a time. Subscribe so you do not miss the next one.